Hi everyone, welcome to network analysis session. So this is Professor Anil Kumar V from School of Electronics and Communication Engineering, Reva University. So in this session, we'll try to see how to apply KVL and KCL for any given network. So when I'm talking with respect to networks, so majorly if you're very good at Kirchhoff's voltage law and Kirchhoff's current law, given any network, we can easily solve it and we can find the different parameters required. So the first and foremost thing that will be seen today is with respect to your Kirchhoff's voltage law. So that is your KVL. So your KVL stands for Kirchhoff's voltage law. So it's, what does it state? It states the sum of voltages within a within a closed loop within a closed loop is is equal to is equal to 0, right? So that's what your Kirchhoff voltage law states. If I take a simple circuit where I'll have one voltage source with two resistors, so I'll take the voltage source value as V and the resistors as R1 and R2, right? So while applying KVL, so first thing is we need to identify the loop and it should be a closed loop. So this is a one loop where it's a closed loop, and we need to see if they have given the currents, because if you want to get the voltage, you know the Ohm's law, so that is equal to V is nothing but your I into R. So if you want to get the voltage across a component, we need to know the current that is flowing in the component and the resistance value. So obviously resistance value would have given. So only thing is we need to see whether the current is given or not. So in this loop, they have not given any current, right? And even the direction is not given. So first and foremost thing, we need to indicate the current direction in the loop, and it is assumed always to be in the clockwise direction. So we need to assume the current flowing in the loop to be always in your clockwise direction, and I'll take this current that flows in this loop called as a I1. Now this I1 will flow across R1 as well as R2. Now if I want to apply KVL to this loop, so we need to be worried about the polarities across the terminals or across your components. So across the voltage source, this is a negative polarity and this is your positive polarity. And similarly across your resistors, resistors don't have the polarity, and whatever the direction of current is entering, right? So the current across your R1 is entering in this direction. So entering terminal will be always taken as a positive polarity, the other will be a negative. Similarly across R2, your plus and minus. Now whenever you are applying KVL, either you should consider entering polarities across all the components or leaving polarities across the components. For example, if I take across the voltage source, if I take the entering, so this is what the current is going in this direction across the voltage source. So this is the entering, right? So if I take the entering polarity across the voltage source, I need to consider the entering polarities across the other components as well. So across the voltage source, it is a minus. Across the resistors, it is a plus always by default. So if I start applying KVL, so it's a voltage source. Directly, I can write it as a V. And since the polarity entering is a minus, I'll take it as a minus V. Then I come across the resistor R1 and the entering polarity is plus, and the voltage across the resistor is given as I into R, and the current that is flowing across R1 is I1. Therefore, I can write it as I1 into R1. And similarly, if I come across R2, again it is a positive polarity plus, and the same current flows across R2 as well. So that is I1 into R2, that is equal to 0. So this is the KVL equation we get across any given loop based on the polarities. If I this I have considered with respect to the first sign I have considered. If I consider the same circuit with respect to the second sign, will it match or not? Let me check. So I'll go with respect to the second sign. If I'm going with respect to the second sign across the voltage source, the second sign is what? A plus, right? So hence I'll take it as a plus V. Then across the resistor, the second sign, leaving polarity is a minus. So I'll take it as a minus I1 and R1. Similarly, across R2, the second polarity is minus. So minus I1 into R2, that is equal to 0. So if I rearrange both the equations remain same. Hence, so either when you are taking with respect to the polarities, so across all the components, obviously, always most of the times you take it as a entering sign so that it will be easy for you always. Right? Or if you're confident enough, you can go with respect to the second sign as well, right? But either way, you get the same equation, so which you'll be considering when you apply with respect to the KVL. So if this is a simple loop where you have only one loop with respect to the given network, so let us assume, so when you have multiple loops other than a single loop, right? So let me take one more example. So where you will have a multiple loops with a given circuit. So I'll take a simple circuit where two loops are there. So this is the circuit which I'm considering with respect to the voltage source and the number of loops. So this resistor I'm directly connecting to this terminal. So this is my R1, R2, and R3, and this is the voltage source V. And now if you see this, so you have V, R1 and R3, there is a one loop. Again, R3 and R2, again, there is a one loop, right? So how to apply in such cases when you have multiple loops, right? So first thing, you have easily identified that there are two loops. So what is the first thing? You need to indicate the loop currents, that is I1 in this loop, and this loop you can take it as I2. So if they have not given the currents, if already they have given the loop currents, then no need to worry, you can directly start applying your KVL. So now let us start with respect to KVL to loop I1. So I'll take the first loop for applying your KVL. So again, I told I'll be starting with the first symbol always. The first or entering symbol here, it is a minus across the voltage source. So it will start with a minus V. Then I told across the resistors, it will be always a positive. So that is plus. So the voltage across the resistor is given as I1 into R1. And now again the resistor R3. Now it is again a positive. But here there is a condition where your R3 is connected between both the loops. That means whatever the current flows through or flows across R3, it will be because of the contribution of I1 and I2. And which one you will take it as a positive, which current will take it as a negative. Again, that is one of the important thing. So since you are applying KL for the loop I1, you take that loop current as a positive, and the other loop current you take it as a negative. So that means the loop which I'm considering KVL is for I1, so that is a positive, minus the other loop current I take it as negative. So I1 minus I2, I got the current across R3, and into R3 I get the voltage, so that will be equal to 0. So that is a one equation you get with respect to the KVL to loop 1. Similarly, if I go with respect to KVL to loop I2, if I take across I2, so in the loop I2 you have only two components, that is R3 and R2. So where again your R3 will come in between both the loops. So now since you are applying KVL for the loop I2, so you need to take that loop current as a positive. So that is I2 minus I1 into R3 will get the voltage across your R3 resistor, then plus across R2. So only I2 will flow. So therefore it will be I2 into R2, that will be equal to 0. So these two are the equations you get when you apply KVL for loop 1 and KVL to loop 2. So solving by solving equation 1 and 2, by solving equation 1 and 2, we get the loop currents. Given the voltage source values and the resistor values, we get the values for I1 and I2. So whenever you're going with respect to your KVL, so generally we also call it as a mesh analysis. So where you'll be able to find the loop currents. So hope you're clear with respect to your Kirchhoff's voltage law, right? So now let us move on with respect to Kirchhoff's current law. So now let us move on with respect to your Kirchhoff's current law. So that is with respect to your KCL. So KCL stands for Kirchhoff's current law. So when I'm talking with respect to Kirchhoff's current law, so what does it states, right? So it states that the sum of the sum of currents entering the node will be equal to will be equal to sum of sum of currents leaving the node. So here you can see your Kirchhoff's current law states that the sum of currents entering the node will be equal to sum of currents leaving the node. The major concern with respect to your Kirchhoff's current law, we'll be talking in terms of a node. Similarly, as we see with respect to your KVL, we'll be talking with respect to a mesh or a loop. Here we'll be talking with respect to a node. So when I hear this word node, so when I tell a node, it is a junction where more than two branches or two components are connected. For example, if I take the simple example of these two, so I have here I am taking two branches and here I am taking three branches with two different resistors. So if I take this, right, it is a junction, it is just a junction, it is not a node, right? So if I take here, so you have three components connected at a junction, and hence we call this as a node. And whatever we get here, so that will be a node voltage, and we give it as a V terminal. So where we'll be able to find the voltage across that particular node, right? So this is how you're going to identify the node. So that is one thing. And given any circuit, so you need to always first so identify the number of nodes. First identify the nodes, then indicate the reference node. We need to indicate the reference node. When I tell reference node, it is nothing but your ground node. So when do you call it as a ground node? Where a node with 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 more number of branches connected, For example, if there is a circuit or a network where there are two nodes, one node with three branches and one more node with four branches. So then the node where you have more number of branches, that you need to take it as a ground node or a reference node. So once you indicate the reference node, then give the names for the nodes with respect to with respect to with respect to the with respect to your node voltages, So these are steps you need to follow. So once you indicate the node voltages, then you can start applying. So then you can apply your KCL, right? So these are steps you need to follow whenever you are going with respect to Kirchhoff's current law with respect to solving any network. So once we are clear with this, so now we'll try to see. So, and one more condition you need to be considered with respect to your Kirchhoff's current law. So that is if that is your branch currents, right? If your branch current direction, if your branch current direction is not given, then always assume it to be living. So if the branch currents are not given, you need to assume always the currents to be a living currents. If I see across the node where I mentioned, so I'll be giving here on the above circuit where you have three resistors connected. So we need to assume the currents which are living across the node, since the current directions are not given. So if there is a current source connected to that particular node, so obviously current direction will be given. Then no need to assume it. And one more thing, so always take living currents. Always take the living currents as positive, and entering currents, the currents which are entering the node, you take it as a negative. So these are the two conditions you need to consider whenever you're starting with respect to the KCL. So now let me see a simple circuit with respect to the KCL, how to apply your KCL to the given network. So I'll take two resistors with one resistor across the junction with one voltage source. Right. So this voltage source, I'll take it as a VA, and this is your R1. R2 and this resistor is R3. So now I told you need to identify first the nodes. So the junction where your VA and R1 is connected, so this cannot be a node. Similarly, if I take the junction where your R1, R2 and R3 are connected, since there are three branches, minimum three branches, so this can be a node. So indicate with a dot across the junction. Similarly, where your VA, R3 and again this branch R2 is connected, this bottommost also can be a node. So now in this circuit, we have two nodes with each node having three branches, same number of branches. I told if you want to, first thing is you need to identify the nodes and then indicate the reference node. So if you want to indicate the reference node, I told, so a node with more number of branches. But here if you see, both the nodes are with the same number of branches, then you can take any node as a reference node. But always for ease of simplification or applying the KVL, so always you will take the bottommost node as a reference node. When I tell reference node, it is nothing of ground. So once you indicate the reference node, then indicate the node voltages. So this I will take it as a V1. So V1 is the node voltage across the junction where your R1, R2 and R3 are connected. Now, next is you need to see whether the current direction is given. They are not given any current direction. So what is that you will assume? You will assume all the currents are leaving the node and leaving currents you will take as positive. So that means all the currents you're going to apply KCL will be the positive values. And now if you see one more condition where you have R1 is connected between V1 and the other terminal of R1 is connected to VA. And similarly, if I take R2, R2 is connected between V1 and the other terminal is connected to ground. When I tell ground, that is nothing but your 0 volts, right? So now if I start applying, so if I apply KCL to node V1, if I apply KCL to the node V1, so what is that I can write? So across R1 and I want I. So I told, so if I'm talking in terms of I, you can write it as I is equal to V by R. And since there are two potentials, right? So we'll be taking, always we'll assume the current will flow from higher potential to the lower potential. Higher potential will take it as a positive and the other potential will take it as a negative. So since your current is flowing from V1 to VA, so we'll take it as V1 minus VA, that whole divided by R1, that is the current across your R1 resistor in that branch. Then if I take across R3 plus, since all the currents are leaving, I told all will be a positive, plus now across R3, your R3 is connected between V1 and ground. So you can take it as V1 minus 0 divided by R3, then again plus. So again your R2 is connected between V1 and a ground. So what is that you can write? V1 minus 0 divided by your R2, that is equal to 0. So this is the equation you get across a particular node when there is a single node. When there are multiple nodes similar to this, right? So you will be getting multiple equations. Solving that, you will be able to get the node voltages. So now if I take a simple one more example with multiple nodes. So let me take one more example. So where we'll try to see, we'll have minimum two nodes. Right? So I'll take two resistors and one voltage source. And I'll try to take one more voltage source instead of connecting it to the ground, so that you'll understand how to apply the voltage as well, polarity, considering the polarity. So this I'll take it as a VA voltage. This I'll take it as a VB. So R1, R2, R3, R4 and R5. So these are the, this is a circuit considering. So first thing is you need to identify the nodes. So obviously where junction VA and R1 is connecting, that is not a node. Where your R1, R2 and R4 connecting, yes, that is a node because minimum three branches are connected. Again R2, R3 and R5 are connected. That junction, again this can be a node. Again where your R3 and VB are connecting, it is just a junction. It cannot be a node. And similarly, if you see the bottommost, so VA voltage source, R4, R5 and VB. So these things are just a wires, right? So all are connected to the same junction and this will be a one node. So total in this circuit, you have three nodes, right? So then you need to indicate the reference node. If I see the topmost two nodes, they are with three branches each. And if I see the bottommost node, it has 1, 2, 3, 4. So that is VA, R4, R5 and VB. So there are four branches. So hence you need to take this as your reference node compulsorily without any other option. So this will be a ground. So once you identified the ground, you can give the node voltages as V1 and V2, right? So now, and they are not given the current direction across the component, and there is no current source. So you need to assume all the currents are living, and I told all the living currents, you take it as a positive. So now I'll start applying KCL. So I'll apply KCL at node V1 first. So across V1, how many branches you have? R1, R4, and R2. So now if I take across R1, I told current is living. When I tell current is living, current is flowing from V1 to VA. So what is that you will take? V1 minus VA by R1. I got the current equation with respect to R1 component or R1 branch. Then, since all the currents are living, you are taking it as a positive. Then, so across R4, the current, if I want, it is V1 minus 0, it is a ground, divided by R4. So I can directly write it as V1 by R4. Then again plus, now you have R2. So where is your R2 connected between V1 and V2? And since you are applying KVL, KCL to your node V1, so obviously current is leaving from V1 to V2. So V1 minus V2, that whole divided by R2, and only 3 branches, you got all the 3 current values, so equal to 0. So that will be your equation 1. Similarly, if I apply KCL at node V2, if I apply KCL at node V2, so first component, if I take R2, R2 is between V2 and V1. So what is that you can write? So since you're applying to node V2, so it will be V2 minus V1, that whole divided by R2. Then since all the branch currents are not given, you're assuming all to be living, so positive. So if I take across R5, it is V2 minus ground, right? So it will be just V2 minus 0 by R5. So I can write it as V2 by R5. Then if I take across R3, again plus. So across R3, your R3 is connected between V2 and VB, right? So obviously, what is that we'll take? So we'll take it as V2 minus VB, that whole divided by R3, that will be equal to 0. So this will be your equation 2. So now once you have only 2 nodes other than your reference nodes, so only you'll get 2 equations. So solving equation 1 and 2, we get the node voltages. We get the node voltages. So what are the node voltages? V1 and V2 value given the voltage source values and the resistor values. So we'll get the values for V1 and V2. So once we get V1 and V2, we can find either a current across other component or power across the component. So anything else, whichever is required, you will be able to get the values. So this is with respect to your KCL when you have a single node and when you have a multiple nodes. So how to consider the current equations and how to get your KCL equations, right? So hope you people are clear with your Kirchhoff's voltage law as well as your Kirchhoff's current law and how to apply those laws with respect to any given circuit. So if you have still any queries with respect to any concept, you can just put it on a comment section so that I'll be able to answer back to those questions. So thank you.